Good afternoon from Dhaka, Bangladesh. I'm Altaf Hussain, former professor, Department of Chemistry, University of Dhaka. We were arranging a lecture series on AS and A-level chemistry, and this is the 40th lecture on electrochemistry. Well, we did discuss in the 39th lecture about electrochemistry also. Just to remind you what are the points we discussed there is just what is the redox reactions. That what we also have a lecture on 13th lecture, I suppose, preliminary idea about redox reaction, and this is what is the syllabus of AS level. Now in A level, this has been extended to electrochemistry. So what we did, in the 39th lecture, we discussed about how to determine an amount quantitatively with the help of redox reactions first. And then we discussed about what is electrolysis. And then we discussed about electrochemical cells, if you remember. And then we discussed how to represent a cell diagram and of the different redox reaction. And we also discussed with standard electrode potential and how we built a calomel electrode. That was the lecture on 39th lecture. Now we extend it in the 40th lecture. This is how we use the standard electrode potential. You know that this is what is the symbol of standard electrode potential. So how we use the value of standard electrode potential to predict how easily we can or difficult to oxidize or reduce an event. That's what we can predict. Okay. Well, here we have listed down of electrode potential of half reaction of some of the reactions, showing the which one will be the oxidizing agent, which one will be the reducing agent, etc. Then you see that with these values are listed in order of increasing negative values. And then of each half reaction. This is a half reaction, reversible half reaction. This is another reversible half reaction. And we put this standard electrode potential of this in increasingly negative value. If the negative value is more and more, if the standard electrode potential value is more and more negative, we say this is a strong reducing agent. And similarly, if it is more and more positive value, we say it is a strong oxidizing agent. So that is what is being shown here in this slide. So this is the application of standard electrode potential. But then we'll have some problem to see that only the standard electrode potential cannot predict everything. There are many other points we have to remember. Okay, we go to next slide. And here I have taken a problem. And that is the problem which, if we remember the 39th lecture and this 40th lecture, then including this lecture content, we have a problem. What is the problem? That is, write a cell diagram of a cell based on two half equations given below. This is the half reaction, so two half reactions. And now you are asked that we have to find out the cell diagram of this, or we have to construct a cell diagram of it, and find also the EMF, electromotive force of the cell, and write overall equation which will be occurring. So this is the cell. Now we know this is standard electrode potential of a cell, which is equal to the standard electrode potential of right-hand electrodes and minus left-hand electrodes. Now we have to find out which one is right-hand electrode and which one is left-hand electrode. Okay, then you see that the right-hand electrode should be the one which has got higher positive standard electrode. So this is higher positive electrode. That should be right-hand electrode. But it is in aqueous solution. So we have to make a electrode, and that is what is a shiny platinum electrode is using for this half reaction. Okay, and then since this is the standard electron potential of copper 2 ion plus 2 electrons, and then copper solid is less than that of iron 3 to iron 2, you take this one in the left hand, and therefore this what is the left hand. And if you remember, this is a salt bridge. So if we represent this one, then it is the cell diagram what we are asked to show, that this is the cell diagram. So we have to remember very well that the given value of the standard electrode potential, we check this and find out which one is more positive, and then we keep it in the right, and the less positive one is the left. And then we show the solve bridge. Okay, now using this one, we can find out the standard electrode potential of the cell. So if you remember this, standard electrode potential of the cell is right hand electrode standard electrode potential minus left hand electrode standard potential electrode. So we have right hand electrode. This is the right hand electrode. Okay. So that is the value, and then minus left hand electrode, that's the value, and so in total we have this value. So this is a positive value, and that we can now say the reaction will be from left to right in the direction of the cell diagram. That means reaction will be left to right in the direction of the cell diagram. And overall equation, if we balance this one with electron, that means this reaction we multiply with 2, and then we have got 2 electron, and here we have already 2 electron. If we add these 2, and then we get the cell reaction is like this. What does it mean? The copper is a reducing agent which reduces iron 3, and we get iron 2, and then iron 3 is an oxidizing agent which oxidizes copper metal and gets copper 2 ion. That's what is the problem, and we solve it like this. Okay, we go to the next slide, and next slide says something else then, that we are always saying standard electrode potential should have a concentration of 1 molar of the electrolyte we will have. So if this solution is not 1 molar 1 molar, not 1 molar concentration, then if the concentration is up or low, then we cannot say this is a standard electrode potential. We have to say that this is no longer a standard electron potential, and we symbolize this like this cell, this E cell. Okay, this graph shows how the electrode potential vary with the concentration of a silver ion, and you can see that with concentration of silver ions, it increases. Okay, so that's what we have to use, and that is called Nernst equation to get the E cell value from the standard electrode potential and the reaction. So E cell value, we can see that Nernst equation is this: E cell is equal to standard electrode potential plus RT ln oxidized, concentration of oxidized form, concentration of reduced form, and ZF. That is the Nernst equation. With help of this, we can find out the E cell even if we know the standard electrode potential. Okay, so what is E? I said electrode potential under non-standard conditions. E naught, the standard condition electron potential. R is a gas constant. We know what is the value of Gauss constant. T is the Kelvin temperature. Okay, Z number of electrons transferred in the reactions. F Faraday constant. Unit is coulomb per mole. Ln is the natural logarithm. Concentration of oxidized form refers to concentration of oxidized form of the half equation, and reduced form refers to the reduced form of the half equation. Okay, this is what is the Nernst equation. Using this Nernst equation, we can also find out the electrode potential of which is not non-standard electrode potential. Okay, next slide says something else, that We can simplify this Nernst equation. How? If we take natural logarithm is this and relate it to the log base 10, then we get the relationship ln x is equal to 2.303 log base 10 x. We know it. Okay, the value r, t, and f are constant. So the equation then becomes E is equal to E naught, and this 0.59, it's the constant value, and the Z log 10 base concentration of oxidized species and concentration of reduced species, ratio of oxidized species and reduced species. If we take this equation, or this half equation, and we want to put this in the equation of this form, then we will see that the molar concentration of this F3 aqueous, this is oxidized form, molar concentration is 0.5 molar, and then iron 2, its concentration is 1 molar, so we can put this value here, and then we get this equation. Okay, so for copper, we can reform this one to and then concentration oxidized form, and we have to remember carefully that if the temperature is not 25 degrees Celsius, then we have to use the Nernst equation in full form. We cannot simplify this equation. That remember that we can simplify only if temperature of the reaction is 25 degrees Celsius. That means Kelvin standard temperature. Okay, next slide. We have limitation for prediction of standard electrode potential also. And how we can see this limitation? We can predict with standard electrode potential, as we said, that whether it will be reduced or oxidized in the reaction. But sometimes the reaction is too slow, and that change we cannot observe. We cannot observe, and therefore, this is the limitations of the. We predicted it, but we will see that the reaction is too slow, and therefore we cannot observe. And that means kinetic value also we have to take into consideration, and then we can predict. So this is what is. Let's say an example. If we take copper sulfate solution and bubble hydrogen gas in it, we will see that this is the standard electrode potential. But we will see nothing if we bubble the hydrogen gas because the reaction rate is effectively zero. So this is a problem, I would say, limitations of prediction of reaction, which will be oxidized or reduced using the standard electrode potential. Do remember this? And another prediction is that we always said that we have to consider concentration, 1 molar concentration for standard condition. If we take this example, and we will see that manganese dioxide does not oxidize with 1 molar hydrochloric acid to chlorine. So what happens? We have to see that the concentration of the hydrogen ion concentration should be increased, and therefore we will see that 12 molar hydrochloric acid is needed to see that manganese dioxide is a stronger oxidizing agent than that of chlorine. So these are the things we have to remember. So we have to see the slow reaction rates, non-standard condition will be with the help of concentration and temperature. We have to remember that also. And then we talk about some cell. So lead acid cell, what is storage cell? Let's say this first. This is definitely an electrochemical cell, but it is a reversible chemical changes occurring there, and we use to recharge this cell by an external electric supply. What is a battery then? This is also electrochemical cells, but then we have to have 2 or more electrochemical cells and connected in series, and that is what is battery. You can see an example of, say, a motor car. There we use the battery, and where it is 12 volts we get from this lead acid cells, and there we have several 6 lead acid cells in series, and then use it in battery, as battery of car. Okay, lead acid, how lead acid cell is working, we showed here in the half reaction. The negative terminal will be this reaction and the positive terminal will be this reaction. That means lead plus sulfate ion, we get lead sulfate plus 2 electron, and then lead oxide, sulfate ion, and hydrogen ion, and then 2 electron, we get lead sulfate and things like this. So one thing is to remember this, because lead ion and sulfate ion, it precipitates a solid. And if we do not use a longer time a cell, then we will see that precipitated forms and you cannot recharge it. But then when we recharge it, what happens? This precipitate dissolves and we get back the lead ion and as well as lead dioxide. And that is, we have to remember this. If we don't use this battery cell for a long time, lead acid cells, then we will see that it's no longer charging anymore because of the lead sulfate coarser than thicker, which are deposited in the electrode. Okay, now we go for the next slide. We do remember about lithium cell, or many times we talk about lithium cell, you see, and it is used in mobile phones, laptops, computers, and these lithium battery cells. And one advantage of this lithium battery cell, the metal has a low density, and based on lithium electrodes can be relatively light. This is an advantage, but disadvantage is also there. Chemist researcher have solved this disadvantage too. What is the disadvantage? Lithium is very reactive, and therefore if it reacts with air, it becomes oxides immediately. And similarly, the metal can react rapidly with water also. That is the disadvantage. And we say that you have solved this disadvantage like this. Now you can see this. So how do we solve? We take carbon graphite, you see, as one of the electrode layer, this carbon graphite, and here we have lithium atoms here in lithium atoms, and then lithium atoms migrated this one and it goes to positive electrode, and here we have this layer lattice of manganese dioxide incorporated in lithium ion. The cell reaction is like this, half cycle reaction, and like this, you see, a schematic diagram of lithium battery cell. So we can go for next slide, and that is also, which is a very important one, fuel cells. Okay, fuel cells are electrochemical cells. So far we are talking all are electrochemical cells, but some has got this advantage, some have got that advantage, etc., in which the chemical energy of fuel is converted directly into electrical energy. So far, we didn't see that it's directly converted into electrical energy, but here we'll see that directly converted into electrical. These fuel cells differ from typical electrochemical cells, such as lithium cell or lead acid cells, having a continuous supply of reactants from which to produce a steady electric current. We go for here then. Look into it, that we have porous electrode impregnated with a catalyst. This is a porous electrode impregnated with lithium catalyst. And then we have hydrogen gas coming to it. And this hydrogen gas reacts and we get hydrogen ion, you see, and then electron here. So electron flows through external circuit like this to another porous electrode impregnated with the catalyst. And what is the electrolyte here? Solid polymer electrolyte. Solid polymer. This is solid polymer electrolyte. So a hydrogen oxygen fuel cell operate with a polymer electrolyte that is permeable to protons. Okay. What happens in the negative terminal? Hydrogen gas converted into hydrogen ions and we get 2 electrons, and at the positive terminals, oxygen plus hydrogen ion plus 2 electron gives us water liquid, and the overall reaction is this. If we look to this reaction, we will see that this reaction is occurring acidic media. Acidic media. So how we say that it's a symmetry, this is hydrogen ion, this is hydrogen ion, and therefore you say that this is happening in acidic media. But these fuel cells can be also in alkaline media. And in that case, we change the fuel. That means instead of hydrogen, what you call take alcohol, methanol, for example, and the negative terminal methanol, we get this carbon dioxide and gas, then hydrogen ion and electron, and then the positive terminal. This is the reaction. And so this reaction is now happening in alkaline condition. So in fuel cell, we can have both acidic condition and also both alkaline condition. Okay, we go to next cell. So far we have discussed the we can talk about lecture number 23, 39, and 40. And these 3 lectures deals with redox reactions as well as electrochemistry. We have finished that chapter, and in the next chapter, what we will get, we will review what we talked about reaction, how a reaction goes. We take quantitative aspect of reaction, rate and data gathered from experiment of rates of reaction, and that's what we will take in the next lecture, next 1 or 2 lectures, and this is what is chemical kinetics. We have discussed chemical kinetics in AS level. With the knowledge of AS level chemical kinetics, we will also now extend this knowledge for A-level chemistry, and we call it reaction kinetics 2. We will take this lecture on the 41st lecture, and maybe we need 2 lectures, 41st and 42nd lecture for reaction kinetics 2. Okay, thank you very much for attending today's lecture. We meet in the next lecture. Thank you all.